So, hi everyone, I'm Kirsty, and I'm really happy to welcome you all to this online course we have today, and thank you all so much for coming. So now I'm really excited to welcome Alison Kiddle and Charlie Gilderdale, who are the speakers for today's session. So thank you both.
Thank you very much, Kirsty. Okay, I'm going to share my screen. Just before we get started though, Charlie and I want to just explain a little bit about what the structure of today's session is going to be. So hopefully you can now see Peaches Today, Peaches Tomorrow, which was one of the problems that we invited people to have a look at if you had time beforehand. Don't worry if you didn't have time to look at it though, because we're going to be talking about it quite a bit. And some of the time we're going to be inviting you to have a go at a little bit of maths and then either share answers in chat or pop your microphones on and share your thoughts and understandings. And some of the time we're going to one of us take the role of the teacher and the other take the role as a pupil to model for you what some of these things might look at in the classroom. And along the way, everything that we use, we're going to show you how to find it on the Enrich website. And then at the very end, Charlie's going to give you a little bit of a tour about how to find some things in more detail. So hopefully by the end of the session, you'll have a really good idea of what Enrich can offer when it comes to fractions and some of the best practice that might be useful when dealing with fractions. Charlie, have I missed anything introductory there, or are we ready to have a look at Peaches?
I think we're ready to go to Peaches.
Okay, well, I'm going to start then just by reading out the first part of the question so that everyone's had a chance to think about it and get their head around it. So if it looks as if I'm looking over here, that's because I've got a second screen that's got the problems on. So my webcam's here, but my screen is there. So it's not that I'm ignoring people, it's just that that's where it is. So the first part of Peaches Today, Peaches Tomorrow then. So we've got a little monkey who had 60 peaches. On the first day, he decided to keep 3/4 of his peaches. He gave the rest away, then he ate one. On the second day, he decided to keep 7/11 of his peaches. He gave the rest away, then he ate one. On the third day, he decided to keep 5/9 of his peaches. He gave the rest away, then he ate one. On the fourth day, he decided to keep 2/7 of his peaches. He gave the rest away, then he ate one. And on the fifth day, he decided to keep 2/3 of his peaches. He gave the rest away, and then he ate one. And the question is, how many did he have at the end? So in thinking about this first part of the question and what we might do in the classroom, this would be a really good opportunity in the classroom just to see where people are at the start of the lesson about fractions. So I'm imagining that you might get everybody to write down their final answer on mini whiteboards. So you might get them to write down some of the intermediate steps on mini whiteboards, and depending on the class you might do it one step at a time, or you might give them some time to work and just do the whole answer. But what might be really nice is to sort of pull together that starting point, to have the teacher modeling the internal dialogue that we might use when we're working out a problem like that. So what I'd like everyone to do as your first task today is to think about the sort of things that you might say as you are working through each stage of this problem, to model the kind of dialogue that you would want students to be saying to themselves as they're working it out. So have a little think, and then you might wish to pop into the chat if you've got anything to share, or you might wish to just pop in the chat to say that you'd quite like to turn your microphone on and speak to us. That would be rather lovely if you did. So Charlie, maybe you'd like to kick us off while people are thinking through how they would solve this problem. What might you say as you are working through the first part of this problem, and what might you write down to go with it if you're writing on the board?
So on the first day, he decided to keep 3/4 of 60 peaches. So I'd be thinking, oh, that means he gave away 1/4 of the peaches, or so 1/4 of 60, I could halve 60 to get 30, and then halve again to get 15. So he's going to give 15 away, which means he's going to keep 45. Then he's going to eat 1, and that's going to leave the monkey with 44. And that's encouraging, because I can see that the next part has got a denominator of 11, and I can see that 44 is a multiple of 11. So,
yeah, I think you're in the top few pupils in my class, Charlie, to have spotted that so quickly. I wonder whether anyone else would have had a slightly different story that they say to themselves when they're working out 3/4 of 60. If you have, pop something in the chat. So my thoughts, Charlie, while you were explaining the way that you did it, is that you worked out 1/4 by halving it and then halving it again. And so that's a really nice strategy for working out quarters, but it's not going to be generalizable for working out everything. So I suspect that the story you would tell for the second day, when you're starting with 44 peaches and keeping 7/11 of them, you might have to tell a slightly different story. And as nobody's shared anything in the chat yet, would you like to share your story for the second day?
okay, so after the first day, I've got 44 peaches, or the monkey's got 44 peaches. He decides to keep 7/11. So this time I'm going to, like you say, there's no advantage to working out how many he's going to give away, the 4/11. So I'm going to work out 7/11 of 44, and I'm going to do that by working out 1/11 first. So 1/11 of 44 peaches. I'm dividing 44 by 11. So 1/11 of 44 peaches is 4 peaches. So if 1/11 is 4 peaches, then 7/11 is going to be 7 times more. So it'll be 28 peaches. So monkey will keep 28 peaches and then eat 1. So we'll be left with 27 peaches.
Okay, and I think this is a really important time to think about recording, because you did a lot there that you could hold in your head all at once. But for some students, there would be intermediate steps there that needed to be written down. Now, unfortunately, 3 minutes before we went live, my graphics tablet stopped working, and so I'm going to have to write with my mouse instead. So I really apologise if things are a little bit wibbly wobbly when I'm annotating today. I'm going to do my best to keep it neat. But yes, it's wonderful when technology lets you down right at the worst possible time. But yeah, so for finding your 7/11, you're finding 7/11 of 44. And so your method to do that was to find 1/11 of 44, which you did by working out 44 divided by 11, for which you got the answer 4. And then to find 7/11, you did 7 times 4 equals 28. And then finally, for the taking away 1, you did the 28, take away 1 equals 27. And so some people might want to have all of those steps written down to see what's going on. And of course, when we write 7/11 of 44, sometimes we would be wanting to change that instead to write 7/11 multiplied by 44, and to have a conversation with students that when we're finding a fraction of an amount, it's written as multiplying that fraction by the amount. But what we've got starting to emerge here is we've got something that we can generalize, because we can talk about whatever that fraction is at the start. We've found 1/11 and then we found 7/11 by multiplying by 7. So then that leads on to find 5/9. What's our strategy going to be for that? So I'm going to insist that people put things in the chat, because I'm starting to suspect that the chat isn't working. So what would my story be for finding 5/9 of 27? What would my first step be? Excellent, the chat is working. Okay, so we're going to start by finding 1/9, and then we multiply by 5 to get 5/9. Brilliant. So rather than
Can I
say,
interrupt you, Alison?
Yep.
You talked about that jumping from 7/11 of 44 and thinking about 1/11 and then thinking about 7/11 to thinking of appreciating that you can replace the of by a multiplication sign. And that feels like quite a leap for many students. Do you want to say a little bit about how one can ease that for them? Because I remember being at school and that felt like a bit of magic to me, and it was never quite clear. So I've used using the language of 7/11 of, and then thinking about it 1/11 of, then it becomes natural. If I'm working at 1/11 of something, it's natural to be dividing that something by 11. And then 7. So whenever I'm doing percentages, for example, if I would work out 27% of something, I work out 1% of it. And I know that's a 100th. And then I can work out 27%, which is 27 times. So I don't think of 27 over 100 times whatever the quantity is. I do the division first and then the multiplication.
And I think that's super important, actually. It brings on to something that's going to be a bit of a theme for today, which is about the language that we use when we're talking about fractions. Because once you've internalized the fact that 7/11 of 44 is the same as the number 7/11 multiplied by 44, and that we can think of 7/11 as being a position on the number line as well as a representation of 7 divided by 11, and as well as 7 pieces out of 11 if I'm cutting up a cake or something. Once you've internalized that, you move freely between all the different representations. But even teaching at secondary level, we will have lots of students whose grasp of this isn't fully developed yet. And at the time when they first meet the idea that 7/11 of 44, sharing 44 into 11 equal parts and taking 7 of them, that gives the same answer as taking the number 7/11 and multiplying it by the number 44. That is actually a massive concept. And so I think this sort of discussion around a problem and saying that every time we do this procedure, every time we find a fraction of an amount, we divide by the denominator to find what 1 is, and then we multiply by the numerator to find out what, in this case, 7 of them are. That's the step that we need to move it on to this multiplicative and dividing relationship. And then, of course, you get into the idea that because division is just multiplication by a reciprocal. Notice the way I said just there, as if this is a really easy concept. But because division and multiplication are these inverse operations and division is equivalent to multiplying by a reciprocal, then I could have done 7/11 of 44 by doing 44 times 7 and then divided by 11. So taking some time to discuss and explore and think about why those two things are the same can also be quite powerful. Now, I talked a lot about language just then. So one challenge I'm going to set everybody is to think over the course of the webinar about any language that we might use in our teaching that describes a procedure that might get in the way of students' conceptual understanding. So what I mean by this is, if I was teaching children how to find a fraction of an amount, I could talk about it by saying, first I want to find 1/11 of 44, and then I want to find 7/11 of 44 by multiplying it by 7. But instead, I might say to find a fraction of an amount, you divide by the denominator and multiply by the numerator, or even you multiply by the numerator and then divide by the denominator. So I might offer it to them as a description of the process, or I might just give it to them as a procedure. And so I want us to be aware and to be on the lookout for times when we might be tempted just to teach the how and not start to explore the why. So Charlie and I thought of some examples of this while we were planning the session, and it will be interesting to see by the end how many of those you can come up with or spot. And obviously, if you spot me and Charlie doing any of those things, you need to call us out on it. Okay, I want to talk a little bit then about what we might do with the rest of Peaches, because we've talked a lot about this language modelling at the start of the problem. So the problem goes on to have this part 2 challenge where we've got 75 peaches and we're going through the same process, keep some, give some away, eat one. These are the fractions that he decided to keep. And there's only one possible order that you can use them in, which will leave you with just one peach at the end. So what we're imagining in the classroom is that people have got the idea of how to work out the fractions of amounts, and this is where they're really starting to practice it. And in the possible support for this activity, so if I scroll up to the top, you can see that there is teachers' resources. In the teachers' resources, I can scroll down to possible support, and it offers you a shorter version of the problem. So after doing this starter, then you'll have some idea of which students are absolutely flying with their fractions and which students maybe need a little bit more support. So you might choose to give the simpler version for students who need a little bit more support, and to be working with them while the rest of the students are trying the main challenge. And then the third part of this is the thing that you often get on Enrich, where you have a sort of like, I wonder what happens if kind of problem. So I wonder how long it would be possible for the peaches to last if the monkey followed these rules. Can you start with fewer than 100 peaches and then choose fractions so there's at least one peach left after a week? So if you didn't get a chance to look at this problem before the session, that might be something you want to go and have a go at afterwards, because it's really quite a nice challenge trying to decide what fractions to use at what stage. And this would make a nice simmering activity to have during a fractions topic, that you introduce this, you maybe set it for a homework, and students can come back and say how long a chain of fractions they managed to make, or you might have it as the thing to do at the end of each lesson. If you've got 5 minutes at the end, just have another go at the peaches choosing fractions. And yeah, so I think that's probably all that I want to say about peaches. Have I missed anything, Charlie? Once you've unmuted yourself.
Only perhaps just to say to people that, yes, it is possible to carry on for well over a week. So we're not going to give away a solution, but
well, there's one here anyway, if people get really stuck.
There are solutions, indeed.
Yeah. Okay, well, for the next problem that I want to look at then, I'm actually going to share something that popped up on my WhatsApp the other day. So I got a message from my dad. Here it is. I'll give people a chance to read it. I'll read it out for you as well. Just so that you know, my dad does a heck of a lot of knitting. He also does amateur radio, but his radio aerials are broken at the moment because of the storms. So he's not been able to play radios. He's had to do knitting instead. So yeah, he sent me this message. Having knitted a number of rounds of my latest sock, I noticed that I have done 1/6 of the total rounds needed. And that if I complete one more round, I will have done a fifth of the work. How many rounds do I need to do in total? So I'm going to see whether the teachers of this workshop can spot the solution to my dad's knitting puzzle as quickly as I did, or even quicker than I did. I think it took me 3 minutes to reply to his message, but I don't think I saw it straight away. So if you think you know how many rounds of knitting my dad needs to make a sock, then drop the answer in the chat. So it looks like Ben was first with an answer there. I think I'd be more interested as well to know what strategies people used. So would anybody like to either explain a strategy in the chat, or if you want to, you can turn your microphone on and talk to us about what you might do to solve this problem. And just for the record, I think you did get it quicker than me. That was only about 40 seconds or so. It was super quick anyway. Ben, how did you work it out?
So you need a sixth and a fifth that are one apart. So effectively, you've got fifth minus a sixth times n needs to be 1. So that's 6 minus 5 over 6 times 5 when you simplify. So n over 30 equals 1, and then times by 30.
Okay, so in your solution there, you used a little bit of algebra. The first thing that you did was turn the problem into maths with your fifths and your sixths, and then you used a little bit of algebra to express the thing that was unknown, and then you manipulated those fractions to find it out. That's lovely. Rika, I don't know if I said your name right. I apologize if I didn't. Did you do it the same way as Ben? You can pop your microphone on or pop it in the chat. I don't mind which. Would you like to just say a little bit about how you worked it out?
Hi, can you hear me? I don't know, I'm in a cafe.
Yeah, no, that's fine.
I used the lowest common multiple of 5 and 6 and then checked back to see it works. It was just a quick go-to.
Okay, so almost
option.
Like a guess and check method.
Yeah.
That if we've got fifths and sixths going on, 30 would be the first number to try, and when you tried it, it worked.
Yeah, basically. I was lucky.
Yeah. Charlie, was that the same way that you did it?
Yes, I think knowing that the total was going to be a multiple of 6 and of 5 suggested that the 30 was a good first port of call.
Sorry, my tea's about to go cold, so I was just trying to swig it all down there. Yeah, so I think sometimes when solving a problem like this, it's really nice to think not just what my first approach for doing it is, but also how might students approach it. And one really good way of figuring out how students will approach it is to give it to some students and see what they do. But obviously with problems on the Enrich website, you can also look at the solutions to see the different ways that students who have tried a problem have done. But quite often there will be an informal way of thinking about a particular case like this that can then be thought about more formally in order to generalize. And this actually makes a really nice introduction. I was very glad that my dad sent me this last week, because it makes a really nice introduction to one of the other problems that we wanted to look at today. So this is the problem, keep it simple. And it's about unit fractions which have numerators of 1, and how you can write some unit fractions as the sum of 2 different unit fractions. So here we've got a half is equal to a third plus a sixth. Now, Charlie thought he'd spotted a rule for this, and he made up some more examples, but not all of Charlie's examples work. So what I'd like you to do is I'd like you to take a quick look at the 4 examples here that Charlie came up with, and just check which ones work and which ones don't. So I'm just going to give you a minute to check those for yourself. So we've got a half is a 10th plus a 20th, a third is a quarter plus a 12th, a third is a 7th plus a 21th, and a quarter is a 5th plus a 20th. Okay, does somebody want to either pop in the chat or pop your microphone on to say which ones you think work and which ones you think don't work of Charlie's 4 examples? So Kieran, I think you spotted what Charlie's rule is. Yes, I saw that you'd written 1 and I realized you meant to write 2 there. So yes, if you're dividing the, so 20 divided by 10 is 2, 12 divided by 4 is 3. So this is the rule that Charlie's using. And so which of the 4 fractions does Charlie's rule actually work for? I mean, I could ask Charlie himself, couldn't I? Charlie, does your rule work for all 4 of your examples?
No, it doesn't.
Okay. What were you playing at?
Well, I was testing out my initial hunch, and then I had to fine-tune it.
Okay, that actually feels like a really mathematical behavior, that you have a conjecture and some conjectures work out and others don't. And so I apologize if I made you feel unsafe and that you don't feel that you can make conjectures anymore. So having revised your conjecture, which of these examples would you say does work and which ones don't work?
So the second one, the one which starts with a third.
And how did you figure out that that worked?
I changed all the fractions into 12ths.
Okay.
So a third is equal to 4 12ths.
Mm-hmm.
A quarter is equal to 3 12ths. And 3
Okay.
12ths plus 1
So
12th.
I'm just going to try and write this down. So on the right hand side, I've got 3 over 12 plus 1 over 12. And that is equal to 4 over 12, which is the same as 1/3. So tick, that works.
And the bottom one also works.
Yeah, and we can write something very similar for that as well. So how would you explain that the other 2 didn't work then?
Well, I could change all the fractions into 20. For the first one, I could change them into 20ths, and very quickly I can see that since 1/10 is 2 20ths, 2 20ths plus 1 20th is going to be nowhere near a half. So I don't have to spend very long worrying about that one.
Okay. So this is about how we convince ourselves of things. And I think with fractions, students often find it very easy to convince themselves of a wrong answer. And so modeling the sort of things that we do when we're proving in order to show that 3 over 20 is definitely not equal to a half. And I think I said to you the other day, Charlie, that I really like the sign for not equal to, and I think it's nice to use it occasionally. And it also helps to separate students who think of equals as meaning the answer is, because if I'm using it as a not equal to sign, it really gets home the idea that it's showing the relationship between 2 numbers. Does that make sense?
Yes, and I also quite, I think when we wrote this problem, we quite liked that Charlie didn't get the rule completely right initially, and that there was, and that this is what mathematicians do. They try things out and then they fine tune.
Okay, so I think having found that 2 of these examples are correct and that 2 of these examples are not correct, so I'm actually going to put a big line through them so that they don't distract us. We might want to try and think, what do the ones that work have in common? And can we conjecture a general rule? So I'm going to give everybody just a little bit of time. So what you might want to do is you might want to try and make a couple more of these of your own that work. So what we want is we want a unit fraction that can be written as the sum of two other unit fractions, but that has this property where the denominators follow this pattern. So I think Kieran mentioned it using the division pattern, but you could also see it as being a multiplication pattern. So 4 times 5 equals 20. And of course, we do have another example of this, because the sock problem is an example of this. So yeah, thank you. So 1/5 equals 1/6 plus 1/30.
Can I just interrupt a second, Alison? I just want everyone to notice that it would be very easy for Alison to have given away the rule and done the thinking for the class, or assumed that now the rule was obvious and it's lovely. It's nice the way that Alison is now saying, okay, come up with some examples of your own, carry on thinking. You don't need me to tell you what the rule is. And everybody then can test whether they're correct or not.
I can see a conjecture in the chat.
A conjecture to me would have a question mark at the end of it, Alison.
So do we think it's not a conjecture? Do we think that it's been proved?
Well,
it's got a question mark now.
And there's a chance that if it was said in a classroom, it might have been said in a way that suggests a little bit of uncertainty.
Yeah, so the language that children might use, that students might use when they're posing a conjecture, they might say something like, I think, I wonder if, could we try? And that's the same sort of language that mathematicians use when they're making a conjecture. I think sometimes we forget that, because the maths that you see written in books has been conjectured and proved, and you see the final product. But when a mathematician writes something down in a book, they've got entire waste paper baskets full of the things that didn't work before they get there, like Charlie's first attempt at the rule here. So once we think we've got a conjecture, so I'm going to just write this out for everybody. So it's 1/x equals, and I'm going to do, this is not standard notation, but I like it. I'm going to do an equals with a question mark over it to say, does this always equal 1/x plus 1 plus 1/x x plus 1. So this follows the pattern of the ones that we've had so far that worked. So we had the 2 and the 3, so the 3 is 1 more than 2, and then the 6 is the product of 2 times 3. We've got 3, 4 is 1 more than 3, 12 is 4 times 3. 4, 5 is 1 more than 4, 20 is 4 times 5, and then 5, 6 is 1 more than 5, and 30 is 5 times 6. So the next thing I might want to do before I try to prove this is to choose an example that's not the next one in line, but maybe uses big numbers. So Charlie, can you tell me a fraction that you want to have a go at writing using this conjecture?
Okay. So I'm going to try and make the arithmetic reasonably easy.
Okay.
But I will still, have you mentioned the term generic example?
I don't think I have spoken about generic examples yet today.
So
are we going to do a generic example?
We're going to do generic,
okay.
Because sometimes, well, if it works for some large, or in this case, very small fraction, then yeah. Okay, so I'm going to try, is it true that 1/99 equals...
I've switched to the whiteboard so that we've got a bit more space. Yep.
Equals 1/100 plus 1 over 9,900.
Okay.
So
how would you go
my
about
assumption
proving
is
that?
that if it works for this, that's going to give me quite a lot of confidence that it might always work.
Okay, so how would you go about proving this?
I would take everything to the right-hand side of the equal sign and turn, so both fractions with a common denominator, so 9,900 as the common denominator. So I'd multiply top and bottom of 1% of 100 by 99.
So I've got 99 times 1 over 9,900. Yeah?
Yes. Plus 1 over 9,900.
And I can do that. I can add those up and get 100 over 9,900.
And then I can divide both the top and the bottom by 100. Because basically, if I'm multiplying the top and the bottom by the same amount, I think of it as multiplying by a fraction which is equivalent to 1. So when you multiplied top and bottom by 99, in effect you're multiplying by 99/99ths.
Yeah.
And then when you divide top and bottom by the same number, you're dividing by 1. So that's why they're equivalent.
Yeah, and I'm really glad, Charlie, that you said divide the top and bottom by 100 rather than saying cancel, because I think cancel is one of those words that we were talking about before, where we throw the word around and it gets used in different ways in different places, because sometimes we use cancelling when we're talking about with fractions and with divisions, but I've also seen people use it when simplifying algebraic expressions. And if you've got a plus x and a minus x, saying that they cancel. And I think sometimes, until you're really secure in your understanding of those concepts, using that language can sometimes get in the way of understanding. So I'm not saying don't use the word cancel, but if you do use it, make sure that it's also emphasized what it is that cancels out. It cancels out because it's a multiplication or a division by 1. Because of course,
the good news is you ended up with 1/99th, which is what we were hoping to end up with, and
yes.
so this has worked. But
this isn't enough to prove it, though, Charlie, is it?
No. But what I like is, and again, like you, I'm not sure whether we're pronouncing Rika's name correctly. The Rika put an algebraic statement. And it might have been very easy for us to say, oh, let's work out whether this is true or not. But instead of doing that, you've treated what Rika wrote as a description and then interpreted that and let me choose a generic example.
And so I think this could happen in the classroom.
The more difficult thing will be to then add those two algebraic fractions, which I know you're about to do.
Yeah.
But I think distinguishing between using that to describe, it's a shorthand of what the rule is, and then also using it to prove that it's always going to work is another step, but a much more demanding step.
Yeah, so I think, in a lot of classrooms, you might have that one child who is quite confident with algebra, who will happily express it algebraically, while other people are still maybe more confident working with numerical examples. So a generic example can be a really good way of making that bridge between the numerical and the algebraic, because what we've actually got on the screen here is we've got the the blueprints. I just realized I had a blue pen for this bit, didn't I? So that's quite nice, actually. But it's the blueprints for the algebraic thing, because we can represent each part of this algebraically. 99 wasn't anything special, it's a big number. So I can turn my 99 into an X, and I can turn my 100 and say, well, what would that be relative to the X? And so I can do the proof by saying that if I have 1 over x plus 1 plus 1 over x plus 1. Well, when I was working with 99ths, what did I do to the first fraction, Charlie?
Can you just fix the plus in the first denominator? Thank you. Okay, so in the first fraction,
So to get from here to here.
Yes, we multiplied the numerator and the denominator by 99, which was the x on the left of the equal sign.
So I need to do multiplying by x to the top and the bottom here. And I'm running out of space, so I would have probably written that on a new line, but I don't want to go off the bottom of the page. And now I've got the same denominator for both the fractions. What happens when I add them together?
Okay, so the next thing you did is you sort of rubbed out the times 1 on the first numerator, because you had 99 and we didn't need the times 1, so then we've just got x, and then we've got the same denominator, so we're going to get x plus 1 over x plus 1.
And then what was my final step?
We divided both sides, both top and bottom, by 100, which was the denominator of the first fraction to the right of the equal sign. So it was the x plus 1.
So I might be tempted to put brackets around my numerator there, because of course we use the fraction line as an implicit bracket for these things, but explicitly putting the brackets in, I think, makes it easier to see what's going on.
I might also be tempted to put a 1 times in front of the x plus 1 in the numerator, so that I can think, oh, it's 1 times that divided by x times that. So I can divide both top and bottom by x plus 1. And I end up with 1 over x, which is what I was hoping I was going to end up with.
Yeah, you're right. With that 1 times there, it makes it really clear what I've got left when I divide, because I think a very common mistake that you see students making sometimes is when they're dividing something by itself, getting 0 instead of 1. And I think, you know, the throwing around the term cancelling can sometimes to add to that a little bit. Okay, so this problem then, let me just switch back to there. So this is called Keep It Simple. It's the first in a set of 3 problems on Enrich, and I want to show you the second problem in the set of 3, which is called Egyptian fractions.
Before you do that, Alison, can we just show them, if you go down a little bit and keep it simple, there's an Alison was surprised, isn't there? Just a little bit.
Oh, yes. Yes.
I think this is just fabulous, because when you first do the first part, you think, okay, well, every unit fraction can be represented by the sum of 2 unit fractions. And now we find that there's more than one way of, so there's a 6 equal to 7th plus a 42. But actually, a 6 is also equal to an 8th plus a 24th. And it's also equal to a 9th plus an 18th. And I think when we first discovered this, we were bold, you know, it was surprising. And I think one of the reasons we liked it is that sort of questions keep bubbling up. Oh, is there something special about a 6? And I think when we've been writing problems, we're always trying to produce context where children are curious and want to go off and explore a bit more.
Yeah. And being able to predict when there's only going to be one way of doing it and when there's going to be lots of ways of doing it. And is it possible to predict how many ways there'll be of doing it? That then becomes the sort of thing where everybody in the class is getting the opportunity to work on some fractions content, but you might have some who are a bit more secure in their fractions content and don't need quite so much practice, but they also have all of these other mathematical things to be getting their teeth into. It's what we mean when we talk about low threshold, high ceiling tasks, because it's something that everybody can make a start on, but that there are all of these generalizations that go up and up and up, way beyond the ceiling. for people to try. So can I show them Egyptian fractions now, please?
You can.
Thank you. Okay, so this is the first follow-on problem to keep it simple. So when you start this problem, you have a way of writing any fraction as the sum of two unit fractions.
So you have a way of representing any unit fraction.
Any unit fraction as
Yep.
the sum of two unit fractions. Yes,
Okay.
yes. So this is explaining the context that it's about how ancient Egyptians wrote fractions, and there's a little bit of an archaeological fudge in here because, of course, they didn't write them the way that we write fractions, but they had a representation, they had a notation for unit fractions. And so if they wanted to represent other fractions, they did it by summing these unit fractions. So this problem is all about how to write fractions with a numerator of 2. So things of the form 2 over n. And I just want people to take a look at the different ways of representing 2/3 that are shown. So we've got a third plus a third, but this isn't allowed because we've got a third repeated. And one of the rules for Egyptian fraction is that they've got to be different unit fractions. So then we've got a third plus a quarter plus a 12th, a third plus a 5th plus a 20th plus a 12th, a third plus a 6th plus a 30th plus a 20th plus a 12th, and so on. So this and so on, when I looked at this the other day, I was thinking, why is it an and so on? What's going on here? So I wonder if anyone who's a little bit quicker than me can spot what's happened in order to find all of these different ways of writing 2/3. So how do we know that if 2/3 is a third plus a third, it is also equal to a third plus a quarter plus a 12th? You got a hint for us, Charlie?
Well, earlier we worked out that a third could be written as a quarter plus a 12th. So I'm looking at that second row. I've got 2/3 equals 1/3 plus a third, but the third has been replaced by a quarter plus a 12th, which is what I learned from the previous problem.
Okay, so I think then I can see how to get the next line from it, because I think the quarter could be written as a 5th plus a 20th. And then the 12th has just gone to the end, yeah. Yes.
So the first fraction and the last fraction have been kept the same. But of course, it could have been just as easily, the 12th could have been changed into 1/13 plus 1 over 156 or something.
Oh, and that's what's happened here on this bottom line, look. Yeah. I mean, that's really lovely, isn't it? Because that means I could keep on doing this forever. I could have an infinitely long number of unit fractions and add them up to get 2/3. Well, maybe not infinitely long.
No, but if you wanted to write 2/3 as the sum of 100 fractions, you could do it. As the sum of 100 unit fractions.
Yeah.
You could do it. And
okay.
That seems surprising. It seems that the power of being able to generalize, and I don't want to do it, but knowing that I can do it is extraordinary.
So if I carry on down the page then, I think this is actually a very good point. Wouldn't it be simpler just to write it as the sum of 2 different unit fractions? Because being able to write it as that really, really long sum is quite a cool party trick, but it's not very efficient. So for 2/3, we've got 2/3 is a half plus a 1/6. And so we're invited to try and find some other fractions with a numerator of 2 that can be written as the sum of 2 different unit fractions. So I'm going to set a bit of a challenge to everybody. I'm going to set you the challenge to see whether you can write the fractions 2/5 and 2/7. I haven't done 2/4 or 2/6 because they cancel, so we already know what's going on with them. So we've got 2/3. Is it possible to write 2/5 as the sum of 2 unit fractions? And is it possible to write 2/7? Now, because we're a little bit short of time, what I'd like you to do is, if your birthday is in the first half of the year, I'd like you to try and find a solution for 2/5. And if your birthday is in the second half of the year, I would like you to try and find a way of writing 2/7. So you want 2 unit fractions that add up to either 2/5 or 2/7, depending if you're a January to June or a July to December. And Charlie, you need to have a go at this as well. So your birthday's in July, isn't it? So you need to do 2/7. My birthday's in April, so I'm going to have a go at 2/5. And we'll all come back together in a couple of minutes and see if any of us have managed to find a way of writing 2/5 and 2/7 as the sum of 2 different unit fractions. If anybody finishes before I bring us back together, then you can have a go at 2/9. Okay, Kieran's got one that works for 2/5, so I'm going to write that up and then we can check it. Has anyone got one for 2/7 yet? So I've got 2/5 equals, and I'm going to put a question mark for now because I still want to check it. It's not that I don't trust you, Kieran. I got the same answer, but we might have made a mistake. You never know. Plus 1/15.
But the important thing, Alison, is that there is no shame in putting a question mark, in remaining in this kind of uncertain. I've sat in so many of John Mason's sessions where one of the first things he says in a session is, I'm going to treat everything that we say, including what I say, as a conjecture, which might need revising.
Yeah, I don't want people to think that an answer is correct or incorrect because I say so. I want them to think an answer is correct or incorrect because maths says so. And if I haven't justified it to convince my class that it's true, I don't want them to take my word for it. I want to have to work harder to convince them, because if they're not convinced, then they're not going to understand. Right, where were we? Okay, so I want 2/7 is the other fraction that we were looking at.
We've had an offer, but unfortunately one of the fractions is not a unit fraction.
Did you do 2/7, Charlie?
I did.
Have you got an answer?
I do.
Is it the same as Theo's?
Yes.
Okay. So again, still a conjecture, 1/4 plus 1/28. And by putting both of these up, what I hope to be able to do is, with Keep It Simple, we used an example to help us to look for commonalities and look for structure that could help us to generalize. So if I work through these two side by side, I wonder whether I'll be able to start seeing what's the same and what's different between these two examples. So to check 1/3 and 1/15, I need to turn them both into 15ths. So 1/3, 3 times 5 is 15. So 1/3 is 5/15ths plus 1/15. So that's 6/15ths, which is.
So here, Alison, you could write both numerator and denominator. So can you write equals 2 times 3 for the numerator and 5 times 3 for the denominator? Because you were talking about cancelling earlier, and people talk about cancelling and the whole thing feels like magic. It just feels mysterious. But if you write it, I know it takes a bit longer to do, but if you write it like this, then it becomes very clear that you've basically got 2/5 and you're multiplying top and bottom by 3. Multiplying top and bottom by 3 is the same as multiplying by 3/3. Multiplying by 3/3 is multiplying by 1. So you cannot bother. And so that is going to equal 2/5.
So let me see if I can do the same for this one. So I've got 28. So I've got 4 times 7 is 28. So I'm going to have 7 over 28 plus 1 over 28. And that's going to be 8 over 28. But I want to get this back into sevenths. So that's going to be 2 times 4 divided by 7 times 4. And hopefully from this, I can start to see things that are common in here and think about what I might do for the next fraction in line. So when I started with 2/5, I ended up with 2/5 times 3 over 3. When I started with 2/7, I ended up with 2/7 times 4 over 4. And so I think if I want to do the one with ninths, I'm going to have 2/9 times 5 over 5, and then see whether I can turn that into something. Did that make any sense at all to anybody other than me? Did that make sense, Charlie?
I have seen this before, and we've talked about this problem when we were planning the session. So
shall I try and express it on a new sheet of paper in a slightly
No, I was going to suggest that you put the circles maybe in a different color around the numbers that you were, so you got the fifths, and we've ended up with 15ths, which was the 5 times 3.
And with the 7ths,
we ended up with 7 times 4. And I think what you were suggesting is, your conjecture was, if we've got 2/9, we're going to end up with 9 times 5.
Yeah. So if I think about odd numbers, 5 is the 3rd odd number, 7 is the 4th odd number, and 9 is the 5th odd number.
Okay.
So I'm going to try this on a new page. So I'm going to start with 2/9, and then I want to have at the bottom that I've got 2 times 5 over 9 times 5, yeah?
That is the conjecture.
That's the conjecture. Okay, so working backwards, that's going to be that I'll have 45ths. So that fraction is going to be 45 there. And then for my other fraction, well, I want to end up with 10 over 45, so it would have to be 9 over 45, because 9 plus 1 is 10. So on this line, I'll have 9 over 45 plus 1 over 45. But then 9 over 45 working backwards is the same as 1/5.
Yes.
So I think that 1/5 plus 1 over 45 equals 2/9.
Okay.
And I could use this one as my generic example, but yeah, we can do exactly the same thing again. We can say, well, how did we construct this example? How can we construct it algebraically? And how can we use that to prove that it always works? Now, I'm aware that we're starting to run short of time. So shall we quickly wrap up Egyptian fractions and then we can move on to something else? Is that okay?
Sure.
Okay, so there is one more problem in the Egyptian fractions family.
Can I just say, Alison, you know, we've done all this a little bit in a hurried way, of course, compared to what we do in the classroom. I think one of the things that I would sort of want to make a case for is just to encourage, to see this with surprise and awe. It just, because the first time you see this, it is surprising. You can write any fraction with 2 as a numerator as a sum of 2 unit fractions. And it's not immediately obvious the first time you see this problem that this is the case. And we haven't done the proof, and we could do an algebraic proof, but even if we haven't, we could do it using a generic example. And all of a sudden, I mean, there's a bit of fascination about all that. I mean, this is why these problems, it seems to me, are so interesting, because you're encouraging students to work on fractions. Colin Foster, who we're going to talk about in a second, talks about purposeful practice. And it was a bit like Alison was talking about low threshold, high ceiling tasks. They're doing a lot of calculating with fraction, but there is a bigger question. And let's not minimize the sort of the significance of what Alison's just done here in terms of, actually, she's found, we've had a conjecture and we found a rule, and we haven't quite proved it, but let us assure you that we could have proved it if you'd wanted to. And then there are further questions on Alison's screen there. Oh, are we going to be able to describe every fraction which starts with a 3 as the numerator as a sum of 2 unit fractions? Ooh, and hopefully some students will be, not everybody will be interested, but in the same way as if I was an English teacher, I might read the first chapter of a book to the class and hope that some of them will want to go on and read the rest of the book. Not everyone will, but it might whet the appetite of some students. And I think this is, the value of problems like these. Okay. Yeah. Sorry to slow you down.
No, please don't apologise. Okay, so the follow-up problem to this, the third in the set of 3 Egyptian fractions problems, is the greedy algorithm. We're not going to look at it. It's a very nice one to go away and have a think about it, because it sort of finishes off the story about which fractions can and can't be written as sums of unit fractions. But what I want to share next then is something that Charlie just mentioned, which is a problem that was donated to Enrich by Colin Foster. And if you've never read any of Colin Foster's stuff or been to any of his talks or anything like that, I really would recommend it, because he's made me think very deeply about the decisions that I make as a maths teacher. But yeah, so this particular problem is called Almost One. And I don't necessarily want you to do the problem. Rather, I'd like you to think about how you would do this problem. So the problem is this: you've got 6 fractions, a 1/6, 1/25, 3/5, 3/20, 4/15, and 5/8. And you can use as many of these fractions as you like, but you can only use each fraction once. And what I want you to do is, I want you to add them together to get an answer that is as close to 1 as possible. So take a couple of minutes to think how you would start this task, what you would try, what strategies you would try to get as close to 1 as possible. And once you think you know what strategy you might try, if I was actually going to give you time to work on this rather than, rushing through because I want to talk about the pedagogy behind it, can you sort of sum up in a couple of words what sort of a strategy you might use to approach this problem, and pop it in the chat, please? Okay, so Theo has suggested a strategy of finding the lowest common denominator. Theo, I think that was my strategy when I worked on this problem the other day. I found something that I could rewrite: a 1/6, a 25th, a 5th, 3/5, 3/20, 4/15, and 5/8 with a common denominator. And then I knew that to get it as close to 1 as possible, I needed to make the numerators sum to something that was close to the denominator. And suggestions come in from Sarah. We could convert them to decimals. I find converting to decimals is really useful when I want to get the sense of the size of a fraction. And I've been doing this quite a lot lately for some other work that I've been doing, where I've got answers that are in fractions and I've needed to have a sense of the magnitude of things for sketching graphs and so on. And so being able to quickly convert things into decimals allows you to get a sense of how big they are. And then once they're converted to decimals, then you can be starting to see what they'll be when you add them together and get things that are close to 1. Any other strategies? One thing that we thought of when we were talking about this the other day was to arrange them in size order, which is much easier to do after you've converted them to decimals, because then you can say, well, if I'm trying to get close to 1, then I get a big chunk of the way with one of the larger fractions, and then I try and fill in the gaps with the smaller ones. Charlie, did you use percentages for this?
Yes.
Tell me a little bit about that.
Well, I mean, that's not very different to using decimals, but yes. So I had, the 3/5 was the 60% and the 5/8, 62.5%. So like you said, I might choose one of those as my large starting points and then keep my smallest percentages, my 4%, which is the 25th, for the final stages when I'm wanting just to put that last little building block and decide. So yes, I'm playing around with, and I think the other day I also sort of added them all together and then worked out, well, I can't remember, I haven't done that this afternoon. It added up to something like 188% or something. And then I thought, oh,
so instead of building up to 100, you said, what happens if I've got all of them, and then start taking them away to get down to 100%. I think some students would rather work in percentages than decimals, because you've got bigger numbers. You've got numbers between 1 and 100 rather than numbers between 0 and 1. And I think some people would just be more comfortable for this. But a problem like this shows the benefit of being able to move fluently between fractions, decimals, and percentages, because you get a different sense of how to do this if you're working in fractions, or if you're working in decimals, or if you're working in percentages. And of course, this concept, this particular set of 6 fractions, is a carefully chosen one that you could use, but you could just as easily then repeat this problem with 6 other fractions and with a different target other than 1, or you could have something where there was a target that you could get exactly. I think there's a fractions version of Countdown on Enrich somewhere, isn't there? So if you want students to be doing this playfulness with fractions, there's plenty of opportunities to do it. And so, Charlie, you mentioned very briefly the idea of purposeful practice. I think this is a really, really good problem for that, because in order to answer this problem, you're either going to have to do a lot of equivalent fractions, common denominator, adding fractions, or you're going to have to do a lot of converting to a decimal or percentage. And then if you asked them to express their final answer as a fraction, they'd have to convert back from the decimal or percentage back into a fraction again. So there's all of that practice going on, but it's for a goal, and the students are making decisions about which fractions to add together. So rather than, an exercise that just gives them, 10 sets of fractions to add, where the only thing that they get at the end of it is a tick or a cross, you're giving them something where they're getting the same amount of practice at adding fractions, but they solve a puzzle at the end of it. They get to an answer that has some sort of purpose.
Yeah, so they're not just following a rule. There is an element of following the rule, but there's also an element of choice. about how they go about, what kind of strategy do they have to solve this problem. And that makes it a much more interesting exercise than the exercise which just says, add these fractions together.
Yeah. Now, do we have time to talk about terminating or not, do you think?
Very quickly.
All right.
Oh, by the way, I've got good news.
Yes.
I can write 3/5 as a half plus a tenth.
Oh.
So I can write at least one of the fractions with a 3 in the numerator.
Charlie, have you been sitting doing that while I've been talking about this?
I have been listening.
There's always one student in the class, isn't there? Okay, so we've just talked a little bit about converting between fractions and decimals. One thing that comes up for students slightly older is the idea of turning a recurring decimal into a fraction. And so you have to have this idea of which fractions can and can't be written as terminating or as recurring. So there's a couple of problems on Enrich that aim to tackle that. And I want to talk to you a little bit about this one, terminating or not, which is about whether you can tell just by looking at a fraction whether it will have a finite number of decimal places or whether it will recur forever when you write it as a decimal. And so I wanted to show you a way of introducing this problem, which I think is quite nice. So I'm going to get the whiteboard back up again, and I'm going to think about 40ths. So I'm going to write the fractions 1/40 all the way up to 10/40. And what I want you to do is I want you to put in the chat while I'm writing these up, if you happen to know how to write any of these fractions as a decimal. So we're going to have 1, 2, 3, 4, 5 40ths here. And then I really wish I had my pen. I hate writing without my pen. And then I'm going to have 6 40ths down to 10 40ths on this side. So this could be like a warm-up task at the start of the activity. You could just have students working on their own, maybe on mini whiteboards, writing down the fractions from 1/40 up to 10 40ths, and just write as many of them as decimals as they can in a particular length of time. So are there any of those fractions that you know straight away how to write them as a decimal? If you can spot one, pop it in the chat. I think 10 40ths is quite an easy one to do. I think 4 40ths as well. Right, so Sarah's got 10 40ths for us. It's a quarter, which is 0.25. 2 40ths is a 20th, which is 0.05. Well done, Kieran. Any others?
This is where I find it easier to work in percentages, Alison. So a 20th is 5%, and then I can think of the 5% as 0.05.
See, I don't like percentages, but
No,
that's all right. You do you. So 4 40ths is a 10th, which is 0.1. The nice thing about this is if you're doing it collaboratively as a class, then once you've got a few fitted in, you can start using the ones you know to fill in the ones that you don't know. And so you could, for example, say, well, if I know 2 40ths, how can I use that to work out 1 40th? And then you're encouraging this sort of, it's like number sense, but for fractions. How do they relate to each other? Well, fractions are numbers, Alison, what are you talking about? How they relate to each other. And if you know one, how can you work out another from it? And really cementing those relationships. So if I know that 2 40ths is 0.05, 1 40th must be half of that, which is going to be 0.025. And then once you've got one of them, you can just start doing your 0.025 times table, which of course everybody knows, and you can fill in all of the others. So of course, what's going on here then is all of these are going to be terminating decimals. We're not going to have any recurring decimals from the 40ths. So what you could go on and ask next is, if they've got calculators that they can use, or if they can practice a little bit of division to do it, you can invite students to try out some fractions for themselves. So tell them to write down 10 fractions and then work out what they are as decimals, and then collect them all together on the board and put the ones that recur on one side and the ones that terminate on the other, and then start to look at what they have in common. And so this can be a really nice way to get into why some fractions terminate and some don't. So if I go back to my screen, you can see that in the problem there are 8 fractions suggested there to see which of them terminate and which one recur, and it actually shows you which ones can terminate just there. And of course you can go on and you can read the teacher's notes for this problem and see what we suggest to come next, and to have a look at the solutions that people have done. And then after that, for some students, so you can see this is now an age 14 to 16 problem, challenge level 2 star. So this is a little bit harder, but looking at how you can write a recurring decimal as a fraction. So I want to talk a little bit, I'm going to stop sharing for now. I want to talk just a little bit before I hand over to Charlie to finish off about some of the key messages that we've talked about in this session, just to try and bring it all together. So we've talked quite a bit about purposeful practice, because fluency in fractions is really, really important. Students have got to be able to do these things of adding fractions together, dividing by a fraction, multiplying fractions, simplifying fractions, finding equivalent fractions. There's so much, not just number work, but also in algebra, where you need to be able to spot these things and manipulate them fluently. But that fluency relies on students having the conceptual understanding. If they're just going through the motions, if you teach them that to divide fractions you do keep, change, flip, and then they forget, was it keep, change, flip? Was it flip, change, keep? What was it that I changed? Is this for adding fractions or multiplying fractions? Without the conceptual understanding, if there's jargon, if there's imprecise language, it's going to get in the way of them developing that fluency. And that's when you see them making these silly mistakes, and you just think, well, how can they have written that down? Quite a lot of the time, if they write down some really, what seems like a silly answer to a question, it's just because there's a misconception hiding in there somewhere. And so in order to do that and to develop the conceptual understanding alongside the fluency, you can use this idea of having purposeful practice to do it. So Charlie, would you be able to share your screen with us and just show us where we can find some of these problems that we've looked at today? Would that be okay?
I just want to add to what you were saying, Alison.
Mm-hmm.
It seems to me there's a tension between short-term fluency and long-term fluency. And of course, we can get students to be fluent in today's lesson if we say to them, we're just going to do divisions of fractions today, and this is what you need to do. And at the end of the lesson, all the children can leave having been successful at dividing fractions. But there's no guarantee that along down the road, in a couple of months' time, when you give them a mixed bag of problems to do with fractions, they will know and understand why a particular rule needs to be used for some questions and not for the others. And so having that conceptual understanding hopefully reduces the chance of them using inappropriate algorithms.
Yeah, having the why as well as the how.
Look, I'm happy for you just to share your screen since you've been doing it, and I'll draw.
And you'll direct me. All right, that's fine. So let me do that. Okay, so I've gone to the Enrich homepage here.
Okay.
Oh, advent calendar, that looks fun. Can I click on that?
You can.
Okay, I'm going to do this. You tell everybody about the rest of the website. No, okay.
Okay.
Where do I go to find all the things we've looked at today then?
Okay, so the first thing to say is I will write to Kirsty after the session and send her an email that I'll ask her to forward to everybody with the links to Peaches Today, Peaches Tomorrow.
Keep it simple, Egyptian fractions, almost one, and terminating or not.
Yes, but I will also send a link to where all our problems to do with fractions are, which is in our curriculum mapping document. So if you click on that green lozenge, which says secondary teachers.
Just here?
That's the one.
Okay.
And then on the left-hand box where it says secondary curriculum, there's a link to secondary resources organized by mathematical topics.
That one?
That's the one. And there is a Google document and there's a link to it. And that's got our favorite problems on the different topics. So organized by number, algebra, geometry, and we've got.
Oh, so if I scroll down, fractions, here we are. I'm guessing, yeah, there's Peaches, there's terminating or not, there's repetitiously. Yeah, okay. And and then Egyptian fractions is in the number operations because it's about adding fractions and so on. Yes, is that right?
So it's keep it simple just below.
Oh yes. Okay.
So we've
shown you
a fraction of the fraction problems that we would recommend, but so for a more extensive list, the secondary curriculum mapping document page is the one to go to, and it's also got a nice set of resources on enriching the secondary curriculum, and Alison and I also gathered together some of the resources that influenced most, and we've got a what we think and why we think it page.
And I think if I scroll down here, I can find the article by Colin Foster about purposeful practice and mathematical etudes. And that is a really good read if you're interested more in this approach that Colin suggests. And you can see almost one is mentioned in that article.
So I will send Kirsty a link. I'll send her an email and ask her just to forward that to you. So you don't need to remember any of this. It'll all be there in an email in your inbox in the next couple of days.
Okay, I think that's everything from us then. I hope there's been some useful food for thought in there about fractions. Kirsty's just popped in the chat the short evaluation survey for this session. But thank you very much, everybody, for joining in this afternoon. It's been really lovely to share some of our ideas about fractions with you. And yeah, I hope you have a restful Christmas and New Year once that comes. And just advance warning, we're going to be doing a session on area and perimeter, I think in March, but I can't remember the date exactly. So we hope we'll see some of you then. Thank you very much.